This presentation provides an introduction to the Intelligent Waveform Service and gives an overview of the IWS Workbench. NeuralID's Intelligent Waveform Service, or IWS, is a data reduction and analysis suite designed to accelerate life science research and development. R&D teams use IWS to convert large, raw signal datasets into information suitable for lab notebooks, reports, filings, and further analysis. From discovery through preclinical, clinical, and consumer, NeuralID provides the only collaborative biosignal analytics platform spanning the pharmaceutical life cycle. IWS is a scalable enterprise solution that addresses the industry's productivity crisis. IWS outputs analytics into a standard database. IWS is delivered with a suite of tools and SQL code to generate reports in Excel, IDPS BioBook, and Spotfire. Researchers can now collaborate to train IWS to recognize and measure biosignals via a user-friendly Workbench client. The consolidated knowledge base, stored with analysis templates, becomes a reusable asset. IWS can read and process data in multiple vendor formats, enabling users to manage data from discovery assays through the preclinical and clinical trials to consumer applications. NeuralID's patented Cure technology processes data to produce numerical analytics. IWS processes in minutes what would have taken days before and helps the researcher make better decisions faster. Customer studies have shown a 5 to 10x increase in productivity with a 3 to 5% improvement in the quality of results. IWS is architected for the enterprise. Key elements of the architecture are the Workbench, which supports a wide range of industry-standard data formats. Reusable and shareable tools, which promote rapid development and analysis. The job management tools provide an instant view of analysis progress, in addition to automatic notification via text messaging or email. IWS uses a client-server model where the deployments can be scaled from a single user to multi-users to multi-servers and across the entire enterprise. Oracle, SQL Server, and Postgres are some of the industry-standard databases IWS supports. Reporting tools enable visibility into the analysis with standard spreadsheet tools like Excel or advanced dashboards like IDBS eWorkbook or TIBCO Spotfire. This part of the presentation focuses on the IWS Workbench client. Starting at the beginning, the IWS server automatically loads on PowerUp and is always running. We'll connect to the IWS Workbench by double-clicking the desktop icon. To connect the Workbench to the server, we'll either double-click or click on the Connect icon. After the Workbench is connected to the server, all server information will be displayed. In the upper left-hand corner is the Sites and Servers panel, which displays the status of all the servers and their associated templates. In the lower left is the Jobs panel, which shows the job tree. This tree has the status for all the jobs that have been run on this server. The main area of the screen is a context-sensitive settings display. If a server is selected, the server parameters and settings will be displayed. If an analysis template is displayed, the configuration and revision history is displayed. If a job is displayed, the parameters and statistics about that job are displayed. The first thing we'll need to do is to create an analysis template for handling the data. With the IWS Workbench connected to a server, in this case local, we do this by selecting the server and then right-clicking and selecting New Analysis Template. We'll call this template Workbench Demo, or WB Demo for short, and we'll configure the number of channels to 2, although IWS can support up to 256 channels. The other fields are optional and can be filled out to provide additional information about the experiment. The new template has now been created and is displayed in the Sites and Servers palette. We'll double-click or select the icon to enter setup mode. Notice that the settings look different. This is the Workbench setup window, and will also be the area where we'll work on the waveform data. Looking along the Setup Mode tabs, the Config tab is already displayed. The optional text fields can be modified at this point. However, neither the name nor the number of channels can be altered after the template has been created. Moving right is the Revisions tab. Because IWS was designed to be operated in a GLP environment, all previous versions are always archived and retrievable. In fact, it's fairly difficult to delete any previous templates or results at all. The Input tab defines the waveform data files that will be used while in the workbench. However, different data files can be defined at runtime. IWS supports most common data formats. There are two modes of input: single individual files, or a file set that is a group of individual files that are virtually concatenated together and appear as a single file to IWS. This is extremely helpful when the previously recorded files were broken into 2 GB segments to meet 32-bit window requirements. We'll choose Files and then select Browse. From our sample data folders, we'll locate and select the training file that we'd like to work on. We'll use a T-Wave alternans file, which is a good representation of some pretty challenging clinical data. Once the file is displayed, we'll select it. We may have multiple files available, but only a single file or file set can be accessed during setup. After the file is selected, we'll see the other setup tabs become available. If this file was from a multi-electrode array, there would be a Grid Display tab available also. There is an original or unfiltered view which shows a stacked arrangement of the channels. And there is a filtered view. We'll come back to this view in a moment. The Database tab allows us to direct our analysis output, and the Summary Statistics tab provides information about our local analysis. More on that later. Going back into the Original tab, just the 2 valid channels are displayed. We'll need to make some adjustments to the waveform window. By selecting the Edit Preferences menu, IWS has access to the graphics and display properties. There is control over the colors and time duration of the plot. There is also a selection box for auto-scaling of the waveforms. In the Advanced tab are controls for the height of the channels. We'll change the height to 130 pixels. There are also options for labeling and formatting. Under the Audit tab, there is a checkbox that forces the user to enter a descriptive comment every time a template is saved or resaved. IWS includes standard tools where we can zoom in, zoom out, and zoom by factors of 2. There is also a tool called a probe that returns amplitude and time locations across each channel in the waveform display. IWS also has a graphical ruler type tool that returns the time and amplitude differences between 2 data points. Next, we're going to shift our focus to the Filtered tab. This tab is where any signal processing, machine learning, or pattern recognition takes place. There are currently no filters applied to these channels. Even though we won't use it on this data, IWS includes the ability to add filtering by channel or to all channels, which is referred to as a global filter. To apply a global filter, we'd right-click in between the channels and select Properties and then Global Filter. By right-clicking inside of a channel, the filter would have only been applied to that specific channel. We'd need to add a row. IWS allows filters to be concatenated and cascaded. Here we can see that there are 2 types of filters available: a Savitsky-Golay smoothing filter and a generic low-pass filter with a configurable cutoff frequency. Because we won't be using a filter, we'll cancel out of this. The next step is to create a beat detector, or what NeuralID refers to as a marker. We'll select Add Marker. We'll give it the letter name M for marker. A gradient marker type will be selected, which will key in on the slope of the signal. There are a few parameters that must be entered to define the slope. To determine those parameters, we'll zoom in on one of the beats. Then we'll use the ruler to capture the rise and the run. The numbers from the ruler are entered automatically, but to allow some variation, we'll manually adjust the rise down a little to 0.25 and the run up a little to 0.02. We'll add some suppression at 0.5 seconds, which will prevent noise from triggering the detector. We want to apply this detector to all channels. IWS also has the ability to control the object's graphical attributes. We can set the color, line width, and line style. I'll set a few of my favorites here. After we're finished setting up the marker, we'll click OK to exit marker setup. We'll then click the Analyze button to see our results. We should zoom out and analyze again. You can see that we're finding all of the steep, upward going edges of the signal. Now that the markers are working properly, we're going to add the first pattern. A pattern defines the area used for pattern recognition. Because our goal is to measure the QT and RR intervals, we'll need to detect three important features: the onset of the QRS complex, the max location of the R wave, and the last intercept of the T wave. We'll create patterns to do this. We'll select Add Pattern and draw a box around the QRS complex or spike. We'll give the pattern the name QRS. The names will be important when it comes to reporting. We'll use the registration marker M. Because the marker is to the right of the leading edge of the pattern, we'll use the right marker. We'll apply this pattern to all channels. A loose recognition tolerance of 50 will be set so that the pattern recognition will handle a wide variety of QRS shapes. After the QRS is located, a critical element will be the determination of the Q's onset. We'll select the Metrology tab and enable metrology. There are multiple tools to extract measurement information. We'll discuss several of them and how they can be applied. We'll first select the maximum curvature method to detect the left and right elbows, or the points of maximum curvature on the left and right side. This tool will be used when the widths of objects or gaps must be measured. The max curvature method requires some input parameters depending on the data. These numbers fine-tune the sensitivity to the curve and can be determined experimentally. We'll enter a few generic values that are well suited for this waveform. Left extension 45, left search window 45, right search window 45, right extension 45. There are also sensitivity settings for each side. We'll set both of these to 70. Similar to markers, we can also set graphics attributes such as colors, line widths, and line styles for the patterns. This can be helpful when there is more than one pattern type in use. The last step is to train the pattern. We'll perform a right-click inside the box and select Learn. To verify our settings, we'll test the recognition by performing a local analyze, which processes all the data being displayed. By zooming in, we can see that this is a pretty good determination. We can see that the markers and patterns are being found, and the left and right elbows are being identified. We'll scroll later in the timeline to make sure that we are getting good recognitions. It appears that even with very minimal training, IWS is doing a good job with the detection. We'll now add a second pattern to locate the maximum peak of the QRS. This will be used for the RR interval report. We'll select Add Pattern and draw a narrow box around the QRS peak. We'll give the pattern the name Rmax. We'll continue to use the registration marker M. Because the marker is to the left of the leading edge of the pattern, we'll use the left marker. We will apply this pattern to all channels. A loose recognition tolerance of 50 will be set so that the pattern recognition will handle a wide variety of peak shapes. After the R max pattern is located, we'll need to locate the peak or max. We'll select the Metrology tab and enable Metrology. Next, we'll select the Stats method, which is short for statistics, and then select Max Value. The Stats method is a way of capturing boundary conditions. We'll set graphics attributes to separate it from the QRS pattern. Click OK to exit pattern setup. The last step is to train the pattern. We'll perform a right-click inside the box and select Learn. To verify our settings, we'll test the recognition by performing a local analyze, which will process all the data being displayed. By zooming in, we can see that this is a pretty good determination. The maximum point is being identified. We'll scroll later in the timeline to make sure that we are getting good recognitions. The detections are still looking good. We'll create one more pattern on the T-wave for this demonstration, although you can see how the procedure can be repeated for any part of the waveform. First, zoom in on a T-wave. We'll select Add Pattern and draw a box around the T-wave. We'll give the pattern the name TW. We'll use the registration marker M. Because the marker is to the left of the leading edge of the pattern, we'll use the left marker. We'll apply this pattern to all channels. A loose recognition tolerance of 35 will be set so that the pattern recognition will handle a wide variety of T-wave shapes. After the T-wave is located, we'll need to locate the peak and intercepts. We'll select the Metrology tab and enable Metrology. Next, we'll select Cubic Baseline, which is a curve fitting method to detect the peak and last intercept. This is a good tool for detecting when waveforms depart the isoelectric line. There is a variation of the cubic curve fit, which is the linear baseline. This looks at fewer points and is better when there is a lot of noise before or after the pattern. We'll select the last intercept and the peak values. We'll just use the default settings for the curve fitting parameters. We'll set graphic attributes to separate it from the QRS and R patterns. The last step is to train the pattern. We'll perform a right-click inside the box and select Learn. To verify our settings, we'll test the recognition by performing a local analyze, which will process all the data being displayed. By zooming, we see pretty good results. We can see that the markers and patterns are being found, and the peaks and intercepts are being identified. However, we know that the T-wave will change as the experiment progresses. We'll scroll later in the timeline to make sure we are still getting good recognitions. If we see a T-wave that wasn't recognized, we just drag the pattern TW over the top of it and right-click Learn. It appears that even with minimal training, IWS is doing a good job with the detection. By zooming out, clicking the Analyze button, and then looking at the Summary tab, you can see the times and object count for the displayed data that was analyzed. We'll now move to the Database tab. Before the template can be submitted as a job, we need to define the database that the results will be written into. IWS is compatible with industry standard databases such as Oracle, SQL Server, and Postgres. A temporary name can be given to the database connection. We'll call this one DB. For this job, we'll use a database string name of DSN equal IWS64, which refers to an existing 64-bit Postgres database. After we click on OK, we can test the database connection. Connection test succeeded. We next save the template, fill in a comment when prompted, and exit setup mode. To submit this template as a job, we must first select it. Then we do a right-click and select Run Job. We are presented with some job parameters that can be modified, but for now we're just going to click on Run. The job will move into the job tree, shown in the lower left corner. If the server is available, the job will transition right into the running state. By selecting the job in the job tree, we can review the job parameters and statistics, such as the number of markers, number of patterns, and the number of segments. This job completed in 2 seconds with 280 markers, 277 QRS patterns, 276 RMax patterns, and 225 T-wave patterns. Usually, a discrepancy in the counts is caused by irregular shapes and can be addressed with additional training. For the rest of the results, we'll need to shift over to a reporting tool such as IWS eWorkbook Suite, TIBCO Spotfire, or Microsoft Excel. For this demonstration, we'll start with Excel. NeuralID has developed plugins for our various partners' products that help us analyze the data. We start by selecting Add-ins and then Jobs Analysis. We connect to the database, and we'll select the last job that was run by recognizing the job number and the name, WB Demo. We'll select the report option to be preclinical. There are other reports available for impedance and cardio MEA. We'll select the reports to be QT All Beats. We'll also select to generate the plot and statistics. And Generate. We're being prompted to clear any existing sheets. Yes. The data, sorted by channel, and the plots have been generated. We've created a table that has information about both channels. If we scroll to the right, we'll see the QT intervals plotted. Switching to IWS eWorkbook, you'll notice that we already have several experiments defined, including a QT interval. To import the IWS database results without any transcription errors, we'll just use the data link. We'll create a data link for this table, select the IWS data link, connect to the database, select the last job, WB Demo, and select a report type, in this case QT All Sweeps. Selecting Next will give us a preview of what the table will look like, and we'll choose two-dimensional table and hit Next, Next, and Finish. We can see the completed data in the tables. As we look down the QT information, we notice that one of the QTs is missing. The Workbench launcher allows you to double-click on the launcher link, which will automatically launch IWS into the analysis template and take you to the exact point in time the pattern occurred. We can see that there was a missed T-wave pattern and that we should add some training. This is a great example of the tight integration between IWS and IDBS BioBook. With this presentation, we have demonstrated how NeuralID's IWS easily processes challenging multi-channel preclinical